I think our probably last topic is transfer learning. Currently, majority of the learning framework is for different tasks. Let's learn a different system, or using a different methods, or train a different model. There is no communication between different learned systems. In transfer learning framework, as we have some tasks that we have learned before. We have some knowledge encoded in the system. Is this possible for a new task? Can we reuse some of the knowledge that's been learned before? So that there is some sort of knowledge transfer from previous experience to the current learning task. This method has been used even before the neural networks, but neural networks is certainly a prime candidate to perform transfer learning. So the transfer learning that's been studied before is called instance-based. The idea is quite similar to Boost. Remember when we talked about AdaBoost before? The idea is we can reuse learning result from the previous system. We can simply reweight some of the training examples from the source task and use it to learn the target task. The transfer AdaBoost assumes that source and target data are described by the same set of attributes. However, their distribution are different. The system only going to require you to label a very small amount of the target data. It will use the source data in training. When the source tuple is mislabeled, it will reduce the weight of such tuples, so it will have less effect. Remember, AdaBoost is a ensemble method. It does this weight adjustment. So next time you're going to sample a different set of weight, so that it's going to sample the examples that's more similar to the target data into the next classifier learning process. To me, I don't feel AdaBoost actually transferred the knowledge. I mean, well, you can argue it transferred the knowledge which is encoded in the training example. I think neural networks represent the learning, the transfer learning in a more straightforward way. So remember that at the very beginning of this class that I showed you the convolution network. Where is it? Oh, here, perfect. So in a neural network situation, the learning is encoded in the weights. Here. And in the case of convolution neural network, a lot of process is completed here. So if you have done a good job, if you have successfully trained a model that actually gathers the lines, the colors, the corners, the shape information very well in the feature learning process, you don't want to restart relearn a convolution neural network. You want to use things that has been learned here. All you need to do, so the weights are going to stay the same, but you can actually feed this system new training examples. This new training examples might slightly adjust the weight, but the majority of the weight is going to be stable, that you're reusing the knowledge that you learned from your previous process. and you only need to change the classification layer, which is towards the end of the entire neural network. So your label going to be different. Here you might have a slightly different activation function to produce the final prediction. However, vast majority of the learning, the weights are already encoded here that you can reuse. This is much easier than retrain a convolution neural network. The same idea applies for many other things. I think the key reason that the neural network can support such transfer is because the features learned here are not really, it's not human engineered feature. It's the feature that really represented in graphic database data sets, for example, corners, shapes, and all that. And all semantic relations among text information, for example, those two things, these two terms occurs most often in the same context. They're very similar semantic vectors. Those information can be applied even when you transfer this to a different text class or a different image database. Oh my. Okay, we have 2 minutes of time, 1 minute's time now. Is there any questions I can help you address?
Yeah, maybe I missed that, but as far as I understood, it's like the error correction code or the ensemble methods are using the same method over and over again.
Same learning algorithm over and over again.
But is there like a mixture of different learning algorithms?
You certainly can do that. I don't think it's a requirement in ensemble method that you must use the same. You don't have to use the same algorithm 10,000 times.
Okay.
Similar to that, in code training, the features in some sense are independently trained, and can that be sort of translated to an ensemble kind of variation? This is on slide 121.
Right. The translation is very, very limited in the co-training scenario, where your goal is not to have classifier, you're not trying to converge majority vote. Your idea, you want classifier that make different mistakes. So the one classifier should be very confidently classify a certain type of training examples, where the other classifier want to very confidently classify a different group of training examples. That's the ideal combination of different classifiers in a co-training environment. In the ensemble methods, because we often take the majority vote, the key here is to have a lot of training, lots of classifiers, and hopefully majority vote going to tell us the truth.
So essentially, instead of majority, if one took some variation of confidence of that classifier based on how well they have classified a similar sample before, then would that kind of be similar then to code training?
The thing is, they need to be confident on different types, different training examples. If they are confident on the same training examples, it does not solve the co-training. It does not meet the co-training requirement.
Yes, sorry, I think I wasn't, I should rephrase that. What I was thinking was, if there's certain samples that the classifier has done better on or not so well on. Like, let's say if we're doing an ensemble, instead of on decision trees, we're doing it on SVMs. And they are, you know, if you build a variety of SVMs, and each will have like different data points as their sort of support vector machines in there, if I'm understanding correctly. And then when you have a new sample that maybe near about the ones that are like, you know, you could probably create a distance between the new sample and the SVMs of each of the ensemble SVMs. And perhaps that would allow, and as you said, the key factor here is you want an ensemble where they're not all, so there's not groupthink, right? They're not all saying the same thing.
Exactly, exactly. That's exactly the point. They think differently, and their top choices are correct. That's the two basic requirements for classifier that you want to use in a co-training scenario.
Thank you.
Other questions? Okay, I think that's it for this class.